In this lesson, we will be learning the steps of solving rational equations and understanding the similarities between solving rational equations and linear equations. So this is part 2 of discovering rational equations. In the last video, we talked all about what rational equations are. In this lesson, we're going to learn how to solve them using its basic properties, and in the next one, we will be furthering our knowledge of rational equations by solving word problems with them. So the two learning goals of today is to transform rational equations into linear equations in one variable. That's a key step in learning how to solve rational equations, and to understand the reasons for increasing roots of rational equations. So let's do some review for our introduction. What are the steps of solving linear equations? Well, they are to transpose terms, combine like terms, and to isolate the variable. Now I want you to solve the equation x over 2 minus x plus 1 over 3 equals 1. Well, as you can see, it's a linear equation, and we can solve it using these 3 steps listed up here, which gives us x is equal to 8. So let's begin our chapter on solving rational equations. Can you try to solve this equation? Pause the video and see how you can use knowledge you already know about linear equations to solve rational equations. Okay, so first you need to ask yourself, how can you convert it into a whole equation? Then, how can you remove denominators? Then, what expression should you multiply onto both sides of the equation in order to cancel out the denominators? Finally, what is the basis of this doing? Answer all 4 of these questions and you should be able to solve this rational equation. Now, after solving, what is the key point in this entire process? The key point in this entire process is removing denominators. If we want to convert this into a linear equation of one variable, which is a whole equation, we already know how to do that. The only difference this equation has with whole equations is that it has variables on the denominator. But once we figure out how to remove those denominators, then we know how to solve it because we already know how to solve whole equations or linear equations. So removing denominators is the key point. So first, we need to remove the denominators. The least common multiple of each of these denominators is 30 plus x times 30 minus x. So by multiplying both sides by 30 plus x times 30 minus x, we get 90 times 30 minus x is equal to 60 times 30 plus x. So now you can say that we have a whole equation or a linear equation. After solving, we get x is equal to 6. So, is x is equal to 6 the solution to the equation? How can we be sure? Well, after solving, we still need to double check. By substituting x is equal to 6 into the original equation, the left side becomes 5 over 2, which is equal to the right side. Therefore, x is equal to 6 is the solution to the original function. So here is our conclusion. The basic method of solving rational equations is to convert rational equations into whole equations by removing denominators. So if you're going to take notes, this is the perfect page to do so. The key point is to remove denominators. Let's solve the following equation. 1 over x minus 5 is equal to 10 over x squared minus 25. Now using the steps that we've just talked about, as well as the mindset of removing denominators, pause the video and try to solve this rational equation. This should have been your answer. We can multiply both sides by x plus 5 times x minus 5, which is the least common multiple of each of these unlike denominators. This gives us x plus 5 is equal to 10, so x is equal to 5. But how can we be sure? Well, we double check. By substituting x is equal to 5 into the original function, both values of denominators x minus 5 and x squared minus 25 becomes 0, making the equation 1 over x minus 5 equal to 10 over x squared minus 25 meaningless. So we see that if we substitute this into the original equation, the denominators become 0. Therefore, this means that this rational equation has no solution, because if you have a solution and after you substitute it, the denominators become 0, this equation becomes meaningless if the denominators become 0. So if this happens, it means that this rational equation has no solution. Its solution does not exist. This is why it's so important to double check, because there might be a case where after you substitute it in, the denominator becomes 0. Let's observe the process of removing denominators again. We start with this rational equation. When both sides are multiplied by 30 plus x times 30 minus x, when x is equal to 6, 30 plus x times 30 minus x is not equal to 0. This is what it gives us after. So here is our discovery. When a rational equation is multiplied on both sides with a non-zero expression, the solution of the obtained whole equation is the same as that of the original rational equation. Now let's look at another example. When we start with this first rational equation right here, and we multiply both sides with its denominators LCM, we have x plus 5 is equal to 10. So our discovery is that when a rational equation is multiplied on both sides with an expression equal to 0, the solution of the obtained whole equation is not the same as that of the original rational equation. The solution of the whole equation and the solution of the original rational equation are not the same. This is why you really have to make sure you're double checking. So here is a slide all about testing or double checking solutions of rational equations. Remember, this is a key step that you should not skip. When solving rational equations, the solution of the whole equation obtained after removing the denominator may make the denominator of the original equation 0. So the solution of the rational equation must be checked. Is the solution of this whole equation also the solution of the original rational equation? And how can you double check? So here is our testing method. We can substitute the solution of the whole equation into the least common denominator. If the value of the least common denominator is not 0, then this is the solution. Otherwise, this is not the solution, and that means that the solution to this rational equation does not exist. Knowledge key point. Removing denominators to solve rational equations. We multiplied both sides with the least common denominator. We cancel out the denominators and we convert it into a whole equation. Now that it's in the form of a whole equation, we can just use the steps that we have already learned to solve. We solve the whole equation and we substitute the solution that we get into the least common denominator. If the value of the least common denominator does not become 0, then this is the correct solution. If not, then the solution of this rational equation does not exist. Let's look at this example. We want to solve this rational equation right here. Well, both sides can be multiplied by x times x minus 2, which gives us x is equal to negative 3. Now we double check. Substituting x is equal to negative 3 into the original equation, the left side becomes negative 1 and the right side becomes negative 1 as well. So therefore, x is equal to negative 3 is the solution to the rational equation. Now here is another problem. Pause the video and use the steps of solving rational equations to solve. We can divide both sides by x plus 2 times x minus 2, which gives us x plus 2 is equal to 4. Solved, x is equal to 2. We can check by substituting x is equal to 2 into the original equation. Since the denominators become 0, this rational equation doesn't have a solution. It is meaningless. So to summarize in a block diagram, we start at the top with the rational equation. We remove denominators and this gets us to a whole equation. And then we find the solution to the whole equation, which gets us the form of the variable with its solution. After double checking, we ask ourselves when x is equal to a, is the denominator 0? If it's no, then x is equal to a is the solution to the rational equation. But if the answer to this question is yes, then x is equal to a is not the solution to the rational equation. So again, this is another diagram that you can quickly jot down in your notebook if you're taking notes. This runs through the entire process and procedure of solving rational equations. It works especially well if you are a visual learner. This way you can see all the arrows pointing into the steps and the directions these steps go in. All right, so let's move on to the next slide. Example 2. If the solution to the equation 2x plus a over x minus 1 is equal to 1 is positive, so if this rational equation's solution is positive, then what is the value range of a? Well, here is our analysis. After removing denominators, we get 2x plus a is equal to x minus 1. Solved, x is equal to negative a minus 1. And since we are given that the solution is positive, then x is greater than 0 and x is not equal to 1. Therefore, negative a minus 1 is greater than 0 and negative a minus 1 does not equal 1 solves a is less than negative 1 and x is not equal to negative 2. Therefore, the value range of a is less than negative 1 and at the same time not equal to negative 2. Our answer would be a is less than negative 1 and not equal to 2. Here is our method summary. Find the solution of the equation and then according to the positive or negative of the solution, list the inequalities about the variable to solve. And then pay special attention to the fact that the denominator cannot equal 0. Here is example 3. If there is no solution to rational function 2 over x minus 2 plus mx plus x squared minus 4 is equal to 3 plus x plus 2, find the value of m. And we are already given that there is no solution to this rational equation. Think about what that phrase would mean. Well, we talked earlier about how if the denominator of a fraction is 0, it means that it does not have a solution. So that means in the reverse direction, if a rational equation does not have a solution, it means that one of its denominators becomes 0, or all of its denominators. So here is our analysis. We can first convert the rational equation into a whole equation. Then we discuss the solutions in two cases, as a unilinear equation with no solution and the rational equation has increasing roots. We can multiply both sides by x plus 2 times x minus 2 and get 2 times x plus 2 plus mx is equal to 3 times x minus 2. Therefore, x minus 1 times x is equal to negative 10. So when m minus 1 is equal to 0, this equation has no solution, and m is equal to 1. There are extraneous roots, so x is equal to 2 or x is equal to negative 2. So these are each of the different scenarios that we could come to. When x is equal to 2, we can substitute that in to get m is equal to negative 4. When x is equal to negative 2, we'll substitute it in to get m is equal to 6. So the value of m could be 1, negative 4, or 6. Method summary. The meaning of a rational equation with no solution and a rational equation with increasing roots is different. Rational equations have increasing roots only for the numbers whose simplest common denominator is 0. Rational equations with no solution or only includes numbers whose simplest common denominator is 0, but also includes rational equations converted to whole expressions. Class summary. Today we solved rational equations. It breaks down to two main points, the steps and the reminders. So the steps, with the key point as remove denominators, is to first turn a rational equation into a whole equation, solve the whole equation, and then double check. 3 points to be careful of when solving is that when the denominator is removed, the entire original equation is multiplied. After removing the denominator, when the numerator is a polynomial, no parentheses are added, because the fraction line has the effect of brackets. And remember to double check. This is key and crucial. Double checking may not seem like such an important step, but it is a very important step. This could mean Lesson summary. Today we transformed rational equations into linear equations in one variable. We understood the reasons for increasing roots of the rational equations. If you would, please remember to stay tuned for the final video coming up for this chapter, all about applying rational equations. Thank you so much for watching Three Inquisitive Kids, and we'll see you next time.